What if I told you the technology you probably used this morning to summarize your inbox or write a little code is currently drinking the equivalent water supply of 12 million people?
Wow.
Yeah. Or that while you were marveling at its ability to ace a PhD-level science exam, that exact same system completely failed to understand how to read a physical clock on a wall.
It really is the ultimate paradox of our current tech era, you know? I mean, we've built this infrastructure that is simultaneously the most brilliant entity on the planet and also the most physically disconnected, resource-heavy system we have ever engineered.
Welcome to the deep dive. So, if you're listening to this, you already know that artificial intelligence isn't just a tech story anymore, right? It's the economic story, it's the geopolitical story, and increasingly it's the personal story of your own career.
Yeah, absolutely.
But separating the actual measurable reality from, like, the venture capital hype has become nearly impossible.
Which is exactly why we aren't looking at pitch decks today. We are looking at the empirical data. Specifically, we're diving into the 2026 Artificial Intelligence Index report. This is produced by the Stanford Institute for Human-Centered AI, or HAI.
Right, and just to set the table for why we care about this specific document, this isn't some quick weekend survey. The Stanford HAI team is a massive steering committee of top-tier academic and industry experts.
Exactly.
They've been rigorously tracking the evolution of AI since 2017, and back then, AI was still largely a theoretical construct for the general public.
Right. When they started this index in 2017, the goal was really to bring transparency to a notoriously opaque field. Fast forward to the 2026 report, and what's fascinating here is that the conversation has fundamentally shifted.
Yeah, it really has.
We are no longer forecasting what AI might do in some distant future. We are actually quantifying the disruption that has already happened. The threshold has been crossed.
Okay, let's unpack this. Our mission today is to extract the 12 most critical takeaways from this absolute behemoth of a report.
It is huge.
It's massive. We're going straight past the surface-level talking points and digging into the mechanics of where AI actually is right now, where it's heading, and why it is actively rewriting the rules of global economics, education, and even the power grid holding up the lights in your house.
The best place to start understanding that scale is with the sheer velocity of human adoption. Because if you want to understand the impact, you really have to look at how incredibly fast the public has absorbed these tools into their daily routines.
And the numbers are just staggering. According to the report, generative AI reached 53% global population adoption within 3 years.
That's right.
3 years to hit over half the planet.
That velocity is entirely unprecedented in human history. I mean, if you look at the adoption curves of previous general-purpose technologies, the contrast is stark. The personal computer took decades to reach that level of market penetration.
Right.
And the internet itself, the very infrastructure that allows these AI models to function, took significantly longer to become a daily utility for over half the population.
But the friction was different then, right? With the internet or the smartphone, you had to go to a store, spend hundreds of dollars, physically wire your house, or, put a new piece of hardware in your pocket.
Exactly.
This generative AI rollout bypassed all of that.
Yeah.
It just materialized on the devices we already owned. It piggybacked on the mobile and broadband infrastructure we spent the last 20 years building.
That lack of friction, combined with the immediate, often free utility of the models, is the core mechanism behind that 3-year sprint to 53%.
Yeah, it makes sense.
But the Stanford data reveals a geographical distribution that completely challenges our standard assumptions about technological dominance. Adoption correlates strongly with GDP per capita, which makes logical sense, right? Wealthier nations generally possess more robust digital infrastructure.
But here is the massive curveball in the data. You look at the leaderboard for adoption, and Singapore is sitting at number 1 with 61%.
Wow.
Yeah, and the United Arab Emirates is right behind them at 54%. But the United States, the country where Silicon Valley is located, where the vast majority of these foundation models are actually engineered and headquartered, the U.S. ranks 24th.
Yeah.
At only 28.3% adoption.
It is a striking disconnect between technological creation and societal integration.
How does that actually happen, though? How do you invent the most disruptive technology of the 21st century and then lag behind 24 other countries in actually using it?
Well, it comes down to the mechanics of deployment. In nations like Singapore and the UAE, you frequently see highly centralized, state-supported digital modernization initiatives.
Oh, I see.
When the government decides that AI is a strategic national priority, That directive permeates the public sector, the educational system, and the corporate landscape in a really highly unified push.
Whereas in the US, it's just a completely decentralized free-for-all.
Precisely. U.S. adoption is almost entirely dependent on fragmented corporate integration and individual consumer choice.
Right.
There is no top-down mandate to integrate large language models into daily workflows. Furthermore, the U.S. exhibits a significant cultural hesitance, like a trust deficit regarding data privacy and job security, that creates a massive friction point for broad consumer adoption.
But even with that lower adoption rate in the US, the people who are utilizing these tools are extracting an insane amount of value.
Oh, absolutely.
And this brings us to a concept in the report that I think completely breaks our traditional understanding of the economy. The index estimates that U.S. consumers are deriving $172 billion in value annually from these tools as of early 2026.
That's a huge number.
And the median value per user tripled just between 2025 and 2026.
That $172 billion figure is crucial because it represents a massive blind spot in standard economic measurement. We are talking about the mechanics of consumer surplus.
Explain how that works in this context, because traditional GDP formulas don't really capture free software very well.
They don't capture it at all. Let's say you're a marketing consultant, right? 3 years ago, if you needed to synthesize a 50-page market research report into a 2-page executive summary, you either spent 4 hours of your own billable time doing it, or you paid a junior analyst to do it.
Right. Money changed hands.
Exactly. Money changed hands, or measurable labor hours were expended. That activity was visible to the economy.
But today, I just drag and drop that 50-page PDF into a free AI tool,
Yeah,
and 10 seconds later, I have my summary. I didn't pay anyone.
exactly. The utility was fully realized. You received the exact same or perhaps better end product. But because the tool is provided for free by a tech company attempting to build market share, no financial transaction occurred.
Wow, so it's just invisible.
Therefore, that economic benefit is virtually invisible to traditional GDP yardsticks. When you scale that dynamic across millions of workers coding, writing, analyzing, and tutoring, you generate hundreds of billions of dollars in dark economic value.
But providing $172 billion of free utility to consumers isn't actually free for the companies providing it.
Not at all.
Which brings us to the actual cost of this infrastructure. The servers, the advanced chips, the power grids, the engineering talent. You need unprecedented capital on the back end to make this work.
And that reality is driving an investment surge that is fundamentally altering global capital markets. The numbers in the Stanford Index are just staggering.
Yeah, they are.
Global corporate AI investments reached $581.7 billion in 2025. That is a 130% year-over-year increase.
It's just exploding.
And if we isolate just private investments, we are looking at $344.7 billion, up 127.5%.
I want to stop and look at the geography of those dollars, because this is where the global arms race narrative gets incredibly complicated. If you look purely at the private investment numbers, the U.S. looks like an untouchable juggernaut.
On the surface, yes.
The U.S. private investment sits at $285.9 billion. The next highest country is China, sitting at just $12.4 billion in private investment.
Right.
If you stop reading there, the U.S. is outspending China by a factor of 23 to 1.
But stopping there is a massive analytical error, and the Stanford report explicitly warns against it. Comparing the U.S. and China based solely on private venture capital is a fundamental misunderstanding of how the two different economic systems operate.
Right, because my immediate reaction to a 23 to 1 spending deficit is that the race is already over.
Of course.
There's no way a competitor catches up if they're being outspent by that magnitude. So what is the mechanism that levels the playing field here?
The mechanism is the Chinese reliance on state-directed strategic funding, specifically what are known as government guidance funds. And we need to be very objective here. We are merely analyzing the financial mechanics detailed in the Stanford data, not evaluating the political systems themselves.
Understood. Let's look at the mechanics then. How does a government guidance fund operate differently from a venture capital firm on Sand Hill Road?
Well, a U.S. venture capital firm is driven entirely by market returns. They invest in a startup with the expectation of a massive, rapid return on investment, usually a 10x return within 5 to 7 years via an acquisition or a public offering.
Okay.
This forces U.S. AI development to be highly commercial, highly consumer-facing, and aggressively monetized.
Hence the rush to push out chatbots and enterprise software subscriptions.
Correct. Conversely, Chinese government guidance funds are state-initiated pools of capital designed to produce financial returns while explicitly advancing the government's long-term strategic priorities.
Oh, I see.
Between 2000 and 2023, an estimated $912 billion of these funds were deployed across various industries. They operate on much longer time horizons.
Wow, nearly $1 trillion.
Exactly. They aren't necessarily looking for a quick software as a service exit. They are funding foundational industrial scale infrastructure.
So the U.S. relies on hypercharged private capital, demanding fast commercialization, while China utilizes massive state capital, playing a long-term strategic game.
Right.
When you factor in those guidance funds, the 23-to-1 canyon completely vanishes.
It evaporates. And the performance benchmarks in the 2026 index absolutely prove that parity has been achieved. For years, the U.S. enjoyed a comfortable multi-year moat around AI capabilities.
Yeah, we had the biggest models, the best benchmarks, the most citations.
But the report details a highly sobering reality. The era of uncontested U.S. dominance is definitively over.
The timeline on this is wild. The report notes that in February of 2025, a Chinese model called DeepSeek R1 matched the performance of the top U.S. model.
Yes.
And as of March 2026, when this data was compiled, Anthropic's top model, a U.S. flagship, leads the global pack by a margin of just 2.7%.
If we connect this to the bigger picture, a 2.7% performance advantage on an artificial benchmark is virtually a statistical tie when deployed in the real world. You're not going to notice a 2.7% difference in the quality of code generation or data synthesis. The US and China are essentially trading places at the very top of the performance rankings on a month-to-month basis.
But the report does highlight some fascinating divergences in how these two nations are succeeding. Like, the U.S. still holds the crown for producing the top-tier frontier models, and we still hold the highest impact patents. We're building the most advanced theoretical engines.
Yes, but China leads in overall publication volume, total citations, total patent output, and critically industrial robot installations.
Let's linger on that last one because that seems incredibly significant. Industrial robot installations.
It really is.
It goes back to the difference in funding mechanics.
Yeah.
The U.S. is building brilliant software to run in browsers and enterprise suites. China is actively applying the intelligence at scale in the physical manufacturing world.
It is a divergence in application. Two different runners using entirely different metabolic systems for funding and deployment, and they're running neck and neck.
But here is the vulnerability for the U.S. in this race. You can have hundreds of billions in venture capital, and you could build the most advanced frontier models, but you cannot maintain that edge without human capital.
No, you cannot.
You need the mathematicians, the systems architects, the researchers, and according to the index, the U.S. is currently facing a catastrophic structural shift in its talent pool.
This is where the macroeconomic data in the Stanford report suddenly intersects with the personal reality of the workforce. Historically, the U.S. strategy for technological dominance has relied heavily on importing brilliance.
We've historically been the undisputed magnet for top global AI talent.
We didn't just grow the best talent, we vacuumed it up from the rest of the world. But the inflow of that foreign talent is crashing. The report shows an 89% drop in AI scholars moving to the United States since 2017.
That's a massive drop.
And that isn't a gradual decline over a decade. The deceleration is violently sharp. There was an 80% drop in scholarly immigration just in the single year between 2025 and 2026.
Wait, why is that happening so fast? Is it purely immigration policy, or is something else driving this?
It's a confluence of factors, but a major driver is simply the globalization of compute and capability. 10 years ago, if you wanted to work on the absolute cutting edge of neural networks, you almost had to physically relocate to a lab in Silicon Valley or Cambridge, Massachusetts.
Right.
Today, with open source models, decentralized compute resources, and the rise of globally competitive AI labs in Europe, the Middle East, and Asia, top-tier talent no longer has to move to the U.S. to do world-class work.
So if your entire national strategy for maintaining that razor-thin 2.7% lead is dependent on a steady diet of imported genius, and that pipeline drops by 89%, you are facing a massive systemic vulnerability.
Which naturally leads to the question of domestic talent generation. If we aren't importing the talent, we must be aggressively cultivating our own, correct?
Do you think so? But the data reveals a brutal domestic phenomenon that the report calls the entry-level squeeze. AI is generating massive productivity gains for corporations, but the mechanism of those gains involves the direct elimination of junior roles.
We have concrete, empirical data on this now. It's no longer just a fear-mongering forecast. The 2026 report documents that employment among software developers aged 22 to 25 has plummeted by nearly 20% since 2024.
1 in 5 entry-level developer roles vanished in a 24-month window. But the headcount for their older senior colleagues actually grew during that exact same period.
Let's break down the mechanics of why a modern software team operates so differently today than it did 3 years ago. Historically, a senior systems architect would design a complex application.
Okay.
They would then hand the requirements down to a team of 4 or 5 junior developers who would spend a week writing the boilerplate code, setting up the databases, and debugging the basic script.
Right, it was an apprenticeship model. The juniors did the grunt work, learned the architecture, and eventually became seniors themselves.
Exactly. But today, that senior architect doesn't need the team of juniors. They can write a detailed prompt into an advanced coding agent, and the model outputs the boilerplate, runs the unit tests, and commits the code in a matter of minutes.
Wow.
The senior developer just became a 10x engineer. They are drastically more productive, which is why their headcount and value are growing.
But the AI effectively bypassed the entire junior layer of the team.
Yes.
So what does this all mean? It sounds like AI is literally pulling up the ladder behind the senior developers. If the entry-level jobs are automated away, how does a 22-year-old ever acquire the experiential knowledge required to become a 35-year-old senior architect?
That is the structural flaw in the current automation wave, and it extends far beyond software engineering. We see identical patterns in customer service, legal research, and financial analysis. The traditional corporate apprenticeship model of knowledge work is fundamentally breaking.
The report uses a very specific phrase to describe this that I think perfectly encapsulates the anxiety. The disruption is targeted and just beginning.
It is a critical distinction. AI is not currently hollowing out the middle management layer, and it certainly isn't replacing the strategic executive layer. It is explicitly, systematically eating the bottom rungs of the corporate ladder.
And surveyed executives are openly acknowledging that they expect planned headcount reductions in these entry-level areas to actually outpace the recent cuts.
Exactly.
With 1 in 5 junior jobs vanishing and executives planning even more cuts, it is completely logical that everyday people are experiencing profound anxiety about this technology.
The Stanford Index surveyed global public sentiment, and the results illuminate a fascinating psychological paradox.
Tell me about it.
On a global scale, optimism about the benefits of AI has actually risen to 59%. People are highly aware of the utility. They appreciate the $172 billion in consumer surpluses.
Right. They love that it can plan their vacation itinerary or, debug a spreadsheet formula in seconds.
But concurrently, global nervousness is also rising, hitting 52%. We are existing in a state where the public views this technology as a farmy. We love the micro-conveniences, but we are terrified of the macroeconomic implications.
And once again, the United States presents itself as a stark outlier in the data, but this time on the pessimistic end of the spectrum.
Yeah.
Only 33% of Americans believe AI will ultimately make their jobs better, compared to the 40% global average. The prevailing expectation in the U.S. is job elimination.
And when you pair that economic anxiety with the data on institutional trust, you begin to understand the current cultural climate. U.S. trust in the government's ability to effectively regulate AI is sitting at a dismal 31%.
Only 3 in 10 people think the government can manage this transition. Let's view that trust deficit objectively. When a population physically watches entry-level jobs evaporate by 20% in 2 years,
Right.
and they simultaneously realize it cannot rely on their institutions to slow the disruption down, a profound psychological shift occurs.
It's the realization of self-reliance. The public recognizes that the government isn't coming to save them, and traditional corporate structures are no longer willing to train them from the ground up.
Which triggers a massive grassroots survival mechanism. If you're using AI at work, did your bot train you, or did you just figure it out on your own?
Exactly.
For most people, you just mess around with the interface, figure out the quirks, and start quietly using it to keep your head above water.
For the vast majority of the workforce, it is undeniably the latter. We are witnessing a massive self-education boom because formal institutions are completely paralyzed by the velocity of the technology.
The data on the education system is almost comical in its inadequacy. The report states that 4 out of 5 U.S. high school and college students are actively utilizing AI for school-related tasks. It's completely ubiquitous.
Yet only 50% of middle and high schools even possess an official AI policy. And of the teachers attempting to navigate this landscape, a mere 6% say those policies are actually clear or actionable.
It is the literal Wild West in the classroom. The students are wielding tools that the administration is barely authorized to acknowledge, but the scramble to self-educate extends far beyond teenagers cheating on essays. It's reshaping global competitiveness.
Professionals worldwide are desperately acquiring both hard technical skills and soft AI skills, like advanced prompt engineering and workflow integration.
Right.
And remember our earlier discussion about the U.S. lagging at 24th in general consumer adoption?
Yeah.
The index notes that the countries learning AI engineering skills at the absolute fastest rate right now are the United Arab Emirates, Chile, and South Africa.
That is an incredible reordering of the traditional tech map. It proves that the barrier to entry has completely shifted. You don't need a computer science degree from Stanford to leverage these tools effectively.
Not at all.
People in regions that traditionally operated on the periphery of the legacy tech boom are recognizing that AI is a profound equalizer. They're bypassing the sluggish formal institutions and taking their economic survival into their own hands.
It's a purely pragmatic response to a shifting landscape. But this global rush to master these models raises a foundational question. What exactly are we mastering?
Good question.
We have this inherent assumption that as a system gets smarter, its intelligence scales linearly across all domains.
Right, the sci-fi assumption. If a computer is smart enough to beat a grandmaster at chess, we assume it's definitely smart enough to make a cup of coffee.
But the Stanford report highlights that this is absolutely not how artificial intelligence operates. We have engineered an intelligence that is incredibly, mind-bendingly brilliant and utterly embarrassingly clumsy at the exact same time.
Here's where it gets really interesting. The capability benchmarks detailed in the 2026 report are a perfect illustration of what computer scientists call Moravec's paradox.
Yes, Moravec's paradox.
I love this concept. Let's spend some time explaining the mechanics of it, because it explains so much of the weirdness we experience using these tools.
Hans Moravec, along with researchers like Rodney Brooks and Marvin Minsky, observed in the 1980s that high-level reasoning things like advanced mathematics, logic, or playing chess requires relatively little computational power.
Okay.
But low-level sensor motor skills, things like balancing on two legs, recognizing a face in a crowded room, or manipulating a physical object, require enormous computational resources.
So what feels hard to us is easy for the machine. And what feels completely automatic to us is nearly impossible for the machine.
Precisely. And the Stanford data puts hard numbers to this paradox. Let's look at what the frontier models are currently acing. They are meeting or exceeding human expert capabilities on PhD-level science questions.
Right.
They are dominating multimodal reasoning benchmarks. They are successfully winning mathematical Olympiads.
And it isn't just answering static test questions anymore. Their ability to act as autonomous agents, meaning they can read a digital environment, form a multi-step plan, and execute actions without human intervention has skyrocketed.
It has.
There is a benchmark in the report called Terminal Bench. It tests an AI agent's ability to handle complex, real-world computer tasks within a terminal interface. In 2025, agents succeeded roughly 20% of the time. Today, that success rate has leaped to 77.3%.
That is an explosive jump in reliability in a 12-month window. It means the model isn't just generating code, it is actively exploring the operating system, recognizing errors, and dynamically adjusting its strategy to achieve a goal.
And the cybersecurity numbers are even more intense. Agents handling complex cybersecurity operations jumped from a 15% success rate in 2024 to an astonishing 93% today.
Let's linger on the implications of that 93% figure. In a cybersecurity context, an autonomous agent can monitor network traffic, identify an anomalous intrusion pattern, trace the origin, write a custom patch to close the vulnerability, and deploy it all within seconds, with 93% accuracy.
Wow.
It operates at a speed and precision that human security teams simply cannot match.
It's a PhD-level mathematician, an elite systems architect, and an automated cybersecurity defense grid.
Ugh.
But, and this is where Moravec's paradox comes crashing back in, What does this superintelligence actually fail at?
It fails at tasks a neurotypical human toddler accomplishes with ease.
Right.
It still deeply struggles to learn concepts merely by watching a video.
Right.
It cannot consistently generate video content that remains physically coherent over time. The underlying physics engines hallucinate bizarre geometry. It struggles with multi-step planning that requires an innate understanding of the physical world.
My favorite stat in the entire report.
Yeah.
The most advanced neural networks on Earth cannot reliably figure out how to tell time on an analog clock face.
It lacks the grounded physical context required to interpret the spatial relationship of the hands. And if you attempt to embody that intelligence, if you place the AI into a robotic chassis to perform physical chores in a dynamic environment, the failure rate is staggering.
Yeah, the report notes that robots only succeed at roughly 12% of real-world household tasks, such as folding laundry or safely washing dishes. Wait, so the paradox is that evolutionary biology spent millions of years teaching human brains how to balance gravity, how to judge the tactile friction of a ceramic plate covered in soap, and how to manipulate a soft, unpredictable fabric like a t-shirt.
Exactly.
Evolution spent virtually zero time teaching us calculus.
Exactly. We view folding a shirt as easy because millions of years of evolutionary engineering are handling the computation subconsciously. We view calculus as hard because it is a recent, abstract, conscious effort.
But the AI has the exact opposite architecture. It is a disembodied pattern recognition engine trained on the sum total of human text and digital logic.
Yes.
It has the calculator, but it has no body. So manipulating text to solve calculus is trivial, while understanding the physical friction required to fold a shirt is a monumental, nearly insurmountable processing task.
Which is why, for the foreseeable future, plumbers and electricians have significantly more job security than entry-level software developers.
That's a great point.
However, the critical caveat here is that in domains that are purely driven by data, text, and digital logic, the AI isn't just a clumsy assistant anymore. It is rapidly transitioning into a peer.
And nowhere is that transition more profound than in the scientific lab and the medical clinic. The Stanford report shows AI crossing a major threshold here. It is moving from being a glorified spell checker for scientists to actively participating in the discovery process.
In 2026, AI-related publications in the natural, physical, and life sciences grew by 26 to 28% year over year.
And the practical, real-world applications of this growth are breathtaking. The report highlights a milestone in meteorology. For the first time, an AI system successfully ran a full weather forecasting pipeline entirely end-to-end.
Yes, that was huge.
What does that mean mechanically? How did we do it before?
Historically, we relied on massive physics-based supercomputer models. Humans programmed the complex fluid dynamics equations of the atmosphere, and the computers crunched the numbers. But the new AI approach bypasses the human-coded physics entirely. It ingests the raw, messy, real-time meteorological observations from global satellites and sensors, recognizes the massive atmospheric patterns on its own, and directly outputs the final weather predictions. Temperature, wind, humidity faster, and often more accurately than the legacy systems.
It just swallowed the raw telemetry of the planet and spat out the weather forecast.
Similarly, in astronomy, researchers have deployed the first foundation model that is actively automating astronomical observations across 10 different telescopes simultaneously.
Wow.
It isn't just analyzing data after the fact. It is acting as a centralized, autonomous brain, directing a network of physical observatories in real time to track celestial anomalies.
So in the hard sciences, where the data is grounded in physics and mathematics, the models are achieving definitive victories.
Absolutely.
But let's look at what is happening in healthcare, because the report details the medical integration extensively, and it is a much more complicated narrative.
In medicine, AI's most undeniable and widespread victory right now is purely administrative. In 2025, there was a massive adoption wave of ambient clinical intelligence tools.
These are the tools that listen to the doctor-patient conversation and automatically generate the clinical notes for the electronic health record, right?
Correct. And the impact on workflow is profound. Physicians are reporting up to an 83% reduction in the time spent manually writing notes.
That's incredible.
It is a massive blow against the administrative burden that drives so much physician burnout.
Which is fantastic. If my doctor's actually looking at me and listening instead of staring at a laptop screen typing, everybody wins.
Yeah.
But I have to push back heavily on the broader narrative of medical AI here.
Oh, I know where you're going with this.
because there is a huge catch buried in the Stanford data regarding actual medical diagnosis. So it's saving my doctor a ton of paperwork, which is great. But based on that 5% stat in the report, it doesn't actually know how to treat me yet, just how to pass a medical exam.
You are referring to the clinical study data.
Yes. The report analyzed over 500 clinical AI studies to see how well these models actually diagnose patients. And it turns out nearly half of those studies relied on standard multiple-choice medical board exam questions to prove the AI works.
Right.
Only 5% of the studies actually used real, messy patient clinical data.
Your skepticism is entirely validated by the empirical data. There is an enormous barrier between theoretical bench testing and the chaotic reality of human physiology.
Yeah.
It is one thing for a large language model to push a cleanly formatted, logically structured vignette from a medical licensing exam and output the statistically probable correct diagnosis.
Because the exam question is designed to have a single correct answer. It's clean text.
Exactly. It is a completely different beast to feed an AI the sprawling, contradictory, incomplete electronic health record of a 72-year-old patient with 3 overlapping comorbidities, a history of noncompliance with medication, and vague symptoms, and ask it to safely optimize the treatment plan.
The real world is noisy.
The real world is very noisy. Only 5% of the research is daring to test these models against that real-world noise.
So the diagnostic AI is mostly just a really smart medical student taking a written test right now.
Yeah.
It is not Dr. House solving complex, real-world cases.
Currently, that is largely accurate. However, the Stanford Index points toward a rapidly approaching horizon, introducing a concept that is gaining massive momentum in computational biology: the data twin.
I want to spend some time on this because data twin sounds like a concept pulled straight out of a hard sci-fi novel, but the report says the publications on this jumped from near zero in 2015 to 372 in 2025.
It's an explosive area of research.
But what exactly is a data twin?
A data twin is a dynamic, continuously updating computational simulation of an individual human patient.
A simulation of me.
Yes. Imagine a highly sophisticated digital architecture that integrates your unique genomic sequence, your entire longitudinal medical history, and the real-time biometric telemetry from your wearable devices, your heart rate variability, your sleep architecture, your blood glucose levels.
So instead of a doctor looking at a static snapshot of my blood work once a year, they are looking at a continuously running simulation of my specific biology.
Exactly. And the implications for personalized medicine are revolutionary. Before a physician prescribes a new medication, they could run a simulation on your data twin to forecast how your specific metabolism will process the drug over a 10-year horizon.
Wow.
Will it effectively manage your hypertension, or will it trigger a dangerous secondary cardiovascular event in year 7? They optimize the treatment protocol on the digital simulation before they ever introduce a chemical to your actual physical body.
That is the absolute holy grail of healthcare.
Wow.
But it brings up an immediate, glaring red flag for me.
Which is?
If we are moving toward a future where we trust these models to run 10-year simulations on our internal organs, or coordinate arrays of telescopes, or manage national cybersecurity grids, we need absolute certainty regarding how they make their decisions.
Right.
And yet the report shows that we actually know less about how these models work today than we did 3 years ago.
Which brings us to the hidden costs of this entire revolution. We have to discuss opacity and the physical limits of the planet. Let's examine the opacity data first, because it represents a troubling regression in the field.
The index uses something called the Foundation Model Transparency Index, which essentially grades how openly AI companies disclose their internal mechanics. Things like what datasets they use to train the model, how much compute power they used, and their internal risk assessment.
And the average score plummeted. It dropped from an already mediocre 58 last year down to just 40 points this year.
Yeah, it's a massive drop.
The companies building the most capable models, the ones acing the PhD exams, summarizing our medical notes, and supposedly building our data twins, are the exact same companies pulling the curtains closed.
They are locking their training code, their datasets, and their parameter weights inside proprietary black boxes.
If we connect this to the bigger picture, It becomes a profound crisis of systemic trust and the integrity of the scientific method itself. We just discussed how AI is driving breakthroughs in meteorology and biology. But the foundational pillar of the scientific method is reproducibility. A scientist must be able to show their work so peers can independently verify the results.
Right. If you claim you discovered a new protein structure, I need to know exactly how you arrived at that conclusion so I can test it myself.
But if a proprietary, opaque AI model outputs a breakthrough scientific discovery, and the corporation refuses to disclose the training data it learned from or the mathematical weights of its neural pathways, independent verification becomes impossible.
Wow.
We are effectively introducing a foundational layer of unverified proprietary opacity into the bedrock of human knowledge.
It's like having access to a brilliant oracle that gives you the answer to the universe, but the oracle violently refuses to show you its math. You just have to blindly trust it.
And lack of transparency is only one of the hidden costs. We must also address the massive physical footprint required to sustain this illusion of magic.
This is where the narrative really grounds itself in reality.
Yeah.
We use this ethereal metaphor of the cloud. We conceptualize AI as this invisible, weightless grain floating seamlessly in the digital ether.
Yes, we do.
But the Stanford report yanks us right back down to the physical Earth, and the environmental data is incredibly visceral.
The physical infrastructure required is staggering. Let's look at the carbon footprint of just the training phase of a single large model. The report highlights Grok 4. The estimated training emissions for that one model reached 72,816 tons of CO2 equivalent.
To contextualize that number,
Oh.
that is the exact same amount of greenhouse gas you would generate if you drove 17,000 gasoline-powered cars continuously for an entire year.
Exactly.
And that is just the energy expended to train the model before a single consumer ever uses it.
Correct. Once the model is trained, it must be deployed and queried constantly. It has to live in sprawling hyperscale data centers. The Stanford Index documents that AI data center power capacity has now risen to 29.6 gigawatts.
Let me translate 29.6 gigawatts for you. That is roughly equivalent to the total electrical power required to run the entire state of New York at peak demand.
And the constraint isn't merely electricity, it is thermal management. These high-density server racks generate extreme heat while processing complex neural network computation.
Navy cooling.
They require massive industrial-scale water cooling systems. The report notes that the annual water consumption simply for running inference on GPT-4, meaning just the daily queries from users asking it to draft emails or write code, may exceed the drinking water requirements of 12 million human beings.
It is literally drinking the water supply of a major metropolitan area just to keep the servers from melting while we ask it to summarize PDFs. We think of AI as this invisible brain in the cloud, but it's actually drinking the water of 12 million people.
This raises an important question. The cumulative power demand of the entire all-in global AI ecosystem is now comparable to the national electricity consumption of sovereign European nations like Switzerland or Austria.
That is deeply concerning.
Which raises what is arguably the most critical physical constraint on the entire technological trajectory. How sustainable is this paradigm?
Right.
We established at the very beginning of this deep dive that generative AI adoption has hit 53% globally.
Right.
What happens to the global power grid, our water reservoirs, and our climate targets when adoption inevitably pushes toward 100%? What happens to the energy demand when every major hospital system on Earth is continuously running high-fidelity data twins for millions of patients, and every corporate enterprise is running thousands of autonomous cybersecurity agents?
The mathematics of the power grid simply do not compute at the current rate of energy consumption and scaling.
They do not.
It is the ultimate bottleneck. You can generate infinite consumer demand for artificial intelligence, but you are running it on a planet with finite physical resources. The digital brain is outgrowing its physical host.
Well said.
And I think that brings us to the perfect synthesis of everything we've unpacked from this massive data-driven Stanford report. We started by examining a technology that has integrated itself into human society with unprecedented velocity, reaching over half the globe in 3 years and generating hundreds of billions of dollars in invisible economic value.
Yes.
We watched the U.S. and China lock into an incredibly complex, trillion-dollar arms race, where hypercharged venture capital is going head-to-head with massive state-directed strategic funds, effectively erasing the multi-year American lead.
We tracked the collapse of foreign talent pipelines and the sudden, targeted evaporation of entry-level knowledge work, creating a system that is actively pulling up the ladder on the next generation.
And we saw how that disruption sparked a grassroots scramble where everyday people, bypassed by paralyzed educational institutions, are desperately teaching themselves how to survive in a new economy.
Furthermore, we observed a technology that is depthly fundamentally paradoxical in its architecture. It is an intelligence capable of orchestrating networks of astronomical telescopes or autonomously hacking a mainframe with 93% accuracy, yet entirely incapable of reading a clock face or folding a piece of laundry.
It is simultaneously revolutionizing meteorological forecasting and reducing physician burnout, while simultaneously hiding its internal blueprints behind proprietary walls and consuming the electricity of an entire sovereign nation.
So, as we wrap up this deep dive into the 2026 AI Index, I think there is a final thought to consider.
We have spent this entire time talking about the race to build larger parameters, the race to achieve higher benchmark scores, the race to deploy this intelligence globally. But given the massive systemic energy constraints we just outlined and the dangerous regression in transparency, perhaps the true winner of this global AI arms race won't be the country or the corporation that builds the smartest, most massive model.
That's a great point.
Maybe, just maybe, the ultimate victor will be whoever figures out how to make a highly capable, brilliant model run on the energy of a 60-watt light bulb, rather than requiring the energy grid of Switzerland.
It is a profound engineering challenge because that 60-watt light bulb is roughly the biological standard. The human brain, for all its immense complexity, abstract reasoning, and physical adaptability, runs on approximately 20 watts of power.
Wow, 20 watts.
We are currently brute forcing our way towards superintelligence using gigawatts of energy. But until the architecture of artificial intelligence can mimic the elegant efficiency of biological intelligence, our progress will always remain violently tethered to the physical limits of our infrastructure.
That makes perfect sense.
I encourage you, as you interact with these free tools today, whether you are writing a script, analyzing data, or just asking it a question, to keep actively questioning the mechanism. Look past the frictionless magic trick on your screen and consider the vast, physical, resource-heavy machinery churning silently in the background.
Exactly. We might not have a perfectly clean binary picture of what this technology is ultimately doing to our world. The landscape is murky, it's highly complex, and as we've seen, it's full of deep contradictions.
It certainly is.
But thanks to the empirical rigor of reports like this, we at least understand the mechanics of what we are looking at. Thank you for joining us on this deep dive. Stay curious, stay questioning, and we'll catch you next time.